carrying on from where we left off this morning, finding roots using iterative methods, bit of a mouthful. We're going to look this afternoon at the Newton Raphson formula method. Okay. Newton Raphson's formula may be stated as follows. If R1 is the approximate map value of a real root of an equation f of x is equal to 0, so we're looking at the same kind of thing, going to equate something to 0, going to find the roots. Okay. Then a closer approximation to the root, R2, so our second approximation, or next approximation can be found with that formula there. R1 minus the function at the value R1 divided by the value of the first derivative at the value R1. So it involves us differentiating the function so that we can use that formula. Okay? It should be apparent that the method can be used on any function that can be differentiated. So this is the key. We're going to look at the same function as we did this morning, right? And you're going to find out that it actually uses considerably less iterations on that particular example to find the root. The issue there is that function can be easily differentiated. If you don't have either the skill or it's a function that it's not possible to differentiate with your current knowledge, then you can't use this method. You would have to revert back to the method of bisection. Okay, because you don't need any special maths for that, but here you do need to know how to differentiate properly. Okay, so we'll have a look at the same example that we looked at this morning. First of all, using the bisection method is a good way to do it, so we've got some kind of comparison with the two methods. Newton Raphson's, like bisection, also requires an initial estimate to be made. So I'm repeating the information that was in this morning's slides in a way that we've got two ways of doing it. We could draw a graph, and I haven't copied the graph again, because we can look at the function. We look at the function's value at 0. When x is 0, it's minus 17. When x is 1, it's minus 1. But when x is 2, we get a positive value. So we've got a change of sign in the value of that function between x is equal to 1 and x is equal to 2. So we know that we've got a root in that area between those two figures. Okay? Everyone happy with that? That's similar to what we did this morning. So, the second step here is to differentiate the function to find f dash x, the first derivative. Remember, the other way we write that is dy by dx. Is a similar way of writing that function notation. So they're interchangeable. So, find your tables of standard derivatives and differentiate the function 5x squared plus 11x minus 17. Right, so what we got then? We know that to differentiate this function, that's the sum of three things. So we just differentiate each of them separately. So the differential of 5x squared is 10x. And the differential of 11x is 11. Yeah? Okay. So, from that, we've now got the information we need for the formula. So, we could choose to have our first guess as R1. So, we're going to let R1, the first guess, equal 1. We know that we got a root between 1 and 2. We could start with 2. Wouldn't make any difference. Okay? But if we let that equal 1, we already know that the function at 1 was equal to 5 times 1 squared plus 11 times 1 minus 17 equals minus 1. And f dash at 1 is equal to 10 times 1 plus 11, that is equal to 21. Okay, so what we can then say is, by NR method, by the Newton Raphson's method, R2, our second guess at the root, is equal to R1 minus f at R1 over f dash at R1, which is 1 minus 1 over 21. Okay, everybody followed that? So I just put the results here, minus 1 and 21, into the Newton Raphson's formula. And the result of that is 1.048 to 4 significant figures. Just going to check back what the question said with regard to, yeah, we're looking for an answer to 4 significant figures, so we need to keep to 3 significant figures, sorry, so we need to keep at least 4 as we go through the process. And then what we're looking for is we're looking for rounding that to 3 significant figures. So I'm just going to add to that equals 1.05 to 3 significant figures. You may well recognise that from this morning. Yep. Okay. So remember, when you do the bisection method, you're only ever going halfway between the last 2 best guesses. Okay, so this is looking like it's quite quick, because we know what result we got this morning, and I probably ought to find a different example that starts off a little bit further away. Be interesting to see. I'll tell you what we'll do. I'll put the rest of this up. What I want you to do is have a go, starting with a first guess of 2. So go the other side, because 1 gives us a result that was as negative. Start with your first guess being 2 and see how many iterations that takes. So just start the process again from here, but let R1 equal 2 and see what happens then. So, just summarising that example for the video, to use Newton's Raphson's method, the second step you need to do is differentiate the function. So we've got the first differential. Then find the value of the function at the first guess. Here we let R1 equal 1. Find the value of the differential at that. And then plug those numbers into the Newton Raphson's formula there and come up with a new guess. And here, the new guess, we need to keep at least 1 more extra significant figure than we're looking for as a final answer, possibly 2. Okay, each time we'll round it to the number of significant figures we're looking for, because if we get the same rounding to 3 significance twice, that's when we stop iterations. So on to the next page. Second guess starts at 1.048. We put that into the function and get an answer. We put that into the differential of the function and get an answer. All of that then goes into Newton Raphson's formula, giving us a result there. Then rounded to 3 significant figures. We've had the same value twice, 1.05. Therefore, we stop iterations and we can say the root of this we're looking for is 1.05 to 3 significant figures, which is the same answer as we got this morning using the bisection method, but in 2 iterations instead of, what was it, 11, something like that. Okay, so the immediate assertion there is Newton Raphson's is far quicker. I'm going to use it. The only proviso there is that you've got a function that you have the ability to differentiate. Otherwise, you can't do it. Okay, so in essence, I would head for that straight away and say, can I differentiate this? Yes, I can. I'll use Newton Raphson's method, unless I was being asked to do otherwise. Okay, and as you saw in the assignment this morning, I am asking you to compare the 2 methods with a cubic function. Okay. So you also had a go at this problem this morning, one where you were trying to find the point where these 2 functions met, this positive one here. Okay, and again, the first thing we need to do, like we did before, is equate the function to 0. So we've got our function x, f of x as x plus 3 minus e to the x. And we already looked, and we know that our result is between the values of x equals 1 and x equals 2. The other beauty about Newton Raphson's method is you haven't got to watch out for this change of sign thing and make sure you're sharp on that. You just plug the last guess into the formula, put it into the function and calculate the values and come up with a new guess. And then round it to 3 or 4 or 5 significant figures, whatever you're looking for. And all you're doing is looking for where you get the same answer to that number of significant figures twice. It is a much easier one to do with a spreadsheet, because you can just pull the formulas in, copy them down, and as soon as you see no change in the value to 3 or 4 significant figures, you've got your answer. Okay. So have a go at doing that one by Newton Raphson's method. You should be able to differentiate that function x plus 3 minus e to the x, and see how different it was than the number of iterations you took this morning. And I'm going to do, while you're having a go, I'll do a little spreadsheet answer to that one and show you how that would work. All right. Okay, what I've done is in Excel, I've done a spreadsheet version. So in here, in the first column, just numbered the iterations so I can follow where I'm going. This is the first guess in there. Okay, that's the value of the function at first guess. So I've got the value in B2 plus 3 minus the exponent e to the power of whatever's in B2 in that box. This box is 1 minus the exponent of B2. Then I've used R1 minus that value over that value to get a new exact guess, and then in that box round it up to 3 decimal places. And then after you've entered your first guess in that box, the next guess comes from here. So that cell is equal to what's in E2 up here, and then all these formulas are copied down. Then all I'm looking for is the same value twice in that column there, rounded to 3 decimal places, and I've found my root to that number of decimal places. So I could quite quickly see the difference if I'd have started at a first guess of 2 by putting 2 in that box. And actually, if I'd have started at 2, I'd have found it after 4 iterations, one earlier, by starting at 2. Yeah? It is quicker. I can't remember how many iterations we took with the bisection method on that example this morning, but it is quicker. 11, was it? Yeah, so that's half. Okay? So have a go at that logarithmic function one that you done this morning, bisection method. Sorry, Newton Raphson's method. And then, what have you got for f dash? Two over x plus 1, because the f dash of ln x is 1 over x. Yeah, that's 2 times that. Yeah? So either possibly went wrong differentiating, or anyone put plus 2 there, or didn't shift it. You have to equate the function to 0 to use the method. So that you won't get. Is that what you had for the differential? Yeah. No good packing up yet. We've got half an hour to go yet. And oh, you've got to go, haven't you? Yeah, sorry. Practice that we had. Okay. Every night. Bet you love it, don't you? Okay. There are some more there for you to have a go at. Right. That last one's looks tricky because it includes a funny Greek letter called lambda, but it's really no different. Could equally be x. And you've got a cubic in the assignment to do. Okay, but obviously you need to be able to differentiate the functions to be able to do the method.